let's go ahead and get going. Welcome, everyone, to our last Lunch and Learn webinar for 2023. We had quite a bit of interest in this one. Anything PFAS continues to be of interest to our members. So let's get right to it, but a couple of little Zoom etiquette requirements. Everyone should be muted as you join, and I ask you to stay on mute until the end. We can open it up for questions then, and you can unmute yourself and ask them directly. You can also use the Q&A function at the bottom and the chat. I'll keep an eye on both of those, so feel free to type in your questions as you think of them. We are recording this session, and the link will be shared with everyone who registered, along with the slide presentation next week. So let's get going here. Our presenters today are from Heartland Water Technology out of Hudson, Massachusetts. And Heartland's a great NEBRA member with numerous staff actively contributing to our committees. We had them all teed up to do this presentation early in 2023, but they wanted to have more concrete data, especially on the fate of PFAS through this process you're about to hear about, because that's the number one question they knew they would be getting asked by NEBRA members. So I'm going to go ahead, stop sharing my screen. I'll ask Jim to take over here as I introduce our two presenters, Jim Henderson and Brandon Davis. They're both on LinkedIn, so I'm just going to give them brief introductions. You could check out their professional background more. But Jim Henderson is the Director of Business Development for Heartland with over 30 years of experience in the municipal and industrial wastewater industry. His area of expertise is around residual solutions. And prior to Heartland, Jim was the National Director of Industrial Solutions for Synagro, another NEBRA member. He has a Bachelor of Science in Textile Technology from Clemson University. And his co-presenter, Brandon Davis, is the Director of Engineering for Heartland's Gasification Division, where he's spearheading the continued development, optimization, and commercialization of the HelioStorm ultra-high temperature ionic gasifier for a range of waste-to-energy configurations. Brandon joined Heartland during the acquisition of Cogent Energy Systems in 2022. And prior to that, he served in various senior director roles at Ares Clean Energy. Yeah, another NEBRA member. See all these connections? I love it. Brandon has a BS in chemical engineering from the University of Alabama, and he's actually in Tennessee, I believe. So
that's correct. I'm in Murfreesboro.
All right. So Jim, Brandon, take it away, guys.
Well, thank you very much, Janine, and good afternoon, everyone. It's a real honor for us to have the opportunity to speak to everyone today. We think we have a very interesting and compelling technology that supports biosolids conversion in a unique and novel way. And we're very, very interested to talk to you about it today. We're going to go through a few slides here to facilitate the conversation. We're going to introduce our company briefly, but really get right into the technology itself. What it is, how it works, how it functions. Some of the experience that we've got, and talk to you about our approach to bringing it to market, and some of the ways that we think are really essential in terms of validating that technology for our clients. As Janine mentioned, I am business development leader for Heartland's gasification pyrolysis technology, with specific focus on the water residuals vertical. And I'm joined today by Brandon Davis, who will be a co-presenter. Brandon is our Director of Engineering for the Waste Conversion division of our company. And he's going to, as I said, be a co-presenter, and we're ready to address, technical questions, commercial questions that you may have, and looking forward to a nice collaborative conversation. So, a little bit about our company. Heartland was established in 2008, and we, as Janine mentioned, we have traditionally been headquartered in Massachusetts. However, we're going to migrate the company's headquarters to Tennessee, and that will be housed in our newly commissioned technology center, which I'll be describing in much more detail at the end of the presentation. But Heartland is a company that really operates in that space between leachate and disposed traditionally at landfills or at wastewater plants who traditionally have relied on landfills for some of the disposal of their biosolids. And our initial technology, which is depicted here on the left, is our concentrator technology, which is designed for very difficult to treat concentrated wastewater streams. We have decades of success with that technology, and we have installations across the country from Florida to Alaska. Here, most recently, however, we have undertaken, an effort to bring to market a new novel technology around biosolids and residuals, and that's really just the starting point. And we'll be, evolving that toward other feedstocks and other verticals as well. But as we speak with you here today, our focus market-wise is really on the biosolids industry, and we've had a lot of enthusiasm already about the technology, and we're looking forward again to describing it in some detail. But we're going to talk to you about a process really is about biosolids conversion and taking biosolids feedstocks, and converting them to energy and transforming them to materials that are innocuous and valuable for later markets. But the HelioStorm technology that we're going to be talking to you about today, as well as the companion dryer technology, is very novel. The HelioStorm itself was developed through years of dedicated research by Dr. Peter Kong at the Idaho National Labs. And it was really begun as a process to explore nanoparticles and unique and novel ways to develop nanoparticles, nano onions, and other things that I'm not qualified to speak to beyond this. But it has been in development for some decades, and we have acquired the technology just recently, as of last year, and are bringing it to market this year with great success. So here it is. Here is the unit here depicted in the middle of the screen, and as you can see, it's very compact. About the size of a refrigerator, really. And this is a unit, as we'll describe, that is designed to accommodate about up to 4 dry tons of biosolids per day. But it's electrically driven, 480 volt, 3-phase. And we use that to develop and produce multiple plasma arcs that achieve an extraordinarily high temperature of operation within the reactor zone. Again, 3,000 to 10,000 degrees Celsius. And quite honestly, the 10,000 degrees Celsius may be even a bit low, depending on some of the configurations and some of the carrier gases that we might select for that. But again, operating at an extraordinarily high temperature to achieve the performance and the results that are necessary almost instantaneously. The system is scalable, almost infinitely so. Again, we have a design here that is quite capable and adept at accommodating very small volumes, and you can scale this upward, to the capacity that is necessary. It's just a question of coupling these in parallel to one another with sufficient drying capacity. But we believe that the industry will find that very attractive and have great utility for the systems that probably more, there's a lot more smaller systems, and medium-sized systems that describe the industry and define the industry than the very small collection of very large ones, which has really been the hallmark of gasification. Gasification systems are replete through the United States and throughout the world, but they're very large systems typically. This is a unique system in that it's small, compact, and will accommodate a much wider range of applications, and it's very versatile. So this HelioStorm design will accommodate just a wide range of feedstocks, and we'll talk a little bit more about that in a subsequent slide. But not only solid feedstocks, but gaseous feedstocks, and even some very strong potential for even liquid feedstocks, and all of that is dependent upon the desired energy equation that one might prefer. Doing all that, we produce a couple of things. One is a char, which many of you may be already familiar with. But char is the residue, the solid residue of the feedstock that has been introduced, and honestly, it just looks like the residual of charcoal that you get in a bag of Kingsford from your summertime grilling, right? So it's just char. Looks just like that. It's much more uniform and in its form when we produce it. But that really is it, and should be somewhat familiar to everyone. What we're really excited about, though, is HelioStorm's ability to produce a tar-free syngas. Now, syngas is a very valuable byproduct of the process, which we will describe in some detail on how we use it to support the process. But the point here is that our system produces one that is extraordinarily clean, free of tars and other impurities, and does not require the need of an external thermal oxidizer, which is common to many other systems. So the syngas, other than its temperature, is really ready for secondary utilization and to be harvested as a valuable byproduct from the process almost immediately. So let's take it and deconstruct it here just a moment, because it's really interesting in that the HelioStorm is characterized with, it has virtually no moving parts. None of it is made with unobtainium or any exotic parts that are difficult to source in places around the world. It's made of commercially available, readily available materials of construction. And there's very few, if any, real moving parts. There are some wear items that our design allows us to care for and to manage quite easily without interrupting the support of the plant. But here, it's not difficult to crack the code, right? It's a modular system. So one module is a ring, and a ring allows us to tangentially mount opposing electrodes, an anode to a cathode. Those cathodes are placed, into the ring to create a module. We can stack those modules one on top of another to create the plasma fields, which Brandon is going to describe in more detail in just a moment. But this is an M3, right? 3 modules. We call it the M3. These modules can be expanded, sure, but we believe the better way to expand the capacity is to have additional HelioStorm units side by side in parallel operation. We feed the feedstock through the top, and we precondition it with some other plasma torches before it enters the main reaction vessel. We just take a pelletized feedstock, in this case biosolids, feed it through the top. It passes through the reaction zone in the middle through the plasma arcs. And at the bottom, we collect a very small, modest amount of char, and as well as the syngas, right? And we accumulate the char, bring it over to a secondary collection area, and we'll take that syngas and we're going to rechannel it back into the system to support its operation. And we'll talk about that in a bit more detail. But with this, what I'd like to do is ask Brandon to join the conversation now and describe to you the plasma technology that it makes HelioStorm so effective. Brandon?
Sure. So Jim has already sort of introduced the idea of the plasma torch versus the plasma arc. And you can sort of see at the top, the image on the right, that's more of a traditional plasma torch that some of you may be familiar with, where you have an anode and a cathode within a body. You pass a short arc between those two, a carrier gas flows across it and gets heated and ionized, and that comes out as a plasma jet. And it has some advantages, and it's all self-contained, so it's fairly stable. But the way those jets are generally used is that's sort of an indirect way of heating. You take the arc to heat the gas, and then the gas heats whatever material you're trying to convert. And because of the very high temperatures and ionic nature, those gases, those plasma jets tend to be fairly vicious and a little bit hard to get things to mix in with. So the difference with what we do in the HelioStorm is the free burning arc at the bottom, where the anode and cathode are separated across the body of the gasifier, so that the arc is actually thrown across the gasifier and the material falls through that arc and is directly exposed to the electrical arc. And as we mentioned, each module typically has 3 to 4 pairs of those anodes and cathodes on them. And so the way they're arranged is you end up with sort of a pattern of arcs across that, where most of the body of the gasifier is occupied by that high temperature arc, and the material falls through it and then is exposed to that. And so the way we arrange the HelioStorm is we actually have traditional plasma torches at the top to sort of precondition the material as it falls in. So as the biosolids or other feed material comes in, they're exposed to those high temperature plasma jets, and that goes ahead and heats the material up to a temperature where it can start devolatilizing and start doing some pre-gasification. Those plasma jets also provide some thermal ions that flow down into the lower part of the gasifier to make the gasifier a little bit more stable to help support those free burning arcs below. And then the free burning arcs themselves, not only are you having those ions, but you're generating a lot of other ionic materials because of that. You're generating a lot of free electrons and a lot of positive free radicals that then really greatly sort of increase that reaction rate by reacting with the material as it falls through, with the net result being that those arcs will take your feed material and basically decompose them down to their constituent atoms. So if you have a traditional biosolids or other hydrocarbon-like feedstock that falls through, it'll sort of decompose down to carbon, hydrogen, nitrogen, oxygen, the other components. And then as it exits that plasma field, you sort of have a rapid quench that goes on where it recombines into a syngas. And it combines such that the sort of simpler, more stable molecules like hydrogen, nitrogen, carbon monoxide form more quickly. And the rapid quench sort of prevents repolymerization into higher order, species and hydrocarbon. If you go to the next slide, please. So this is leading into sort of a video that shows the HelioStorm in operation. The left side that says ignition, the picture you have is looking down the barrel of the gasifier at the arcs. And so you can see all the anodes and cathodes. You can see the three layers in there. You can see the tips with the electrodes coming off. The interesting thing to me on that one is the center of the picture where it's so bright from the plasma field that it sort of oversaturates the camera image. And, one thing to know about this is you're looking through the darkest welding glass that we can find. And so it's not really green. The green is from the color of the welding glass. But even using the thickest welding glass, darkest welding glass we can find, it's still so hot in the center of that gasifier that it still oversaturates that camera image. And when we play the video in a minute, what you'll see is actually the ignition of the HelioStorm. So the way we light it is in each module, two of the electrodes come together and they touch start, and we pull them back and pull that arc across it. And then the other electrodes light off that arc. And so they don't have to be inserted. They just light off the thermal energy that's being provided by that first pair. On the right side of the image, you'll see a video during actual solids feed. And so again, you can see the glowing from the plasma itself. But the more interesting thing you see is you can see all the little dark spots are biosolids falling into that gasifier. And you can see the trails that they make and the clouds that come off. You can actually see those particles devolatilizing and being reduced in size as they're exposed to that electrical field and generating the syngas. So if you want to play the video. Yeah, so you can see on the left the touch start, and you can see the electrodes pulling back from each other, especially that cathode there on the left. And you can see the other electrodes in that ring lighting off of it. You can begin to see the glow off the tips of them. And then, like we said, on the right side, you can see the pellets falling through and the syngas being generated in the HelioStorm, actually feeding biosolids through it.
Great, Brandon. Thanks very much. I think you're going to continue with this slide.
Yeah. So, as we mentioned, because of the very high temperature and then all the ions and free radicals are being made, you tend to reduce whatever feed material you have down to sort of its constituent atoms, and then it recombines as it comes out of the plasma module. The relevance here to PFAS destruction is that, as you know, PFAS destruction is really a matter of time and temperature. You need sufficient temperature to be able to not only devolatilize the PFAS, but also thermally disassociate it and decompose it. But you also need enough time for that to happen. And there's a relationship between the amount of time you need and the temperatures you're reacting the material. And so it's interesting as you look at other sort of traditional ways of disposing of biosolids, whether it's traditional gasifier or pyrolysis units or incineration, those tend to operate down at temperatures. You know, some pyrolysis units may operate down, even as low as maybe 500 or 600 degrees Celsius. On up to a sweet spot for gasification is probably more like 1250 Fahrenheit, so that you don't cause ash agglomeration in the gasifier. And then sometimes you can have a little bit higher temperatures, up to maybe 1,000 Celsius in some gasification or incineration processes. But you can see that the temperatures and the HelioStorm are much, much higher than that. And so this is where we have that complete PFAS destruction, because you have those very, very high temperatures and that turbulent ionic environment to which they're being exposed, which takes those PFAS compounds as they're volatilized and cracks them down to hydrogen and fluorine and whatever else materials are in the head unit.
Thanks, Brandon. So we also alluded to earlier that our gasifier, like so many others, is preceded by a dryer to properly condition the feedstock that is entering the unit. So there are a range of commercial dryers that everybody on this call, I'm sure, is aware of, and our gasification platform will accommodate literally any pelletized feedstock generated by the commercial units available today. However, we have our own novel design that we're particularly excited about and has generated a tremendous amount of enthusiasm. And this is the LTC Dry unit. Now, LTC stands for low temperature conductive heating. And I'd like to walk you through that in just a moment, but this is sort of a perfect complement to the ultra high temperature ionic gasification. We have an ultra low temperature, low energy drying solution that is a great complement and companion, to that technology, achieving the lowest and most efficient cost of operation. So we begin with a heated pelletized feedstock here. We have a heat exchanger within a silo containing heated pellets, if you will, and they are introduced into a closed augering system here. And as the material, the hot material is augered up, we can begin to introduce dewatered cake, wetter, higher moisture content feedstock into this augering system, right? And so the entire drying zone really is contained the length of that enclosed auger. Very small, very compact, and we think that might accrue to the benefit of permitting and other things, as well as odor control and odor management. But as it augers up, we bring it up, and at this point we can collect the vapor. Now, this system is operating under a vacuum, so we can perform the drying function at a reasonably lower temperature than boiling, conventional atmospheric boiling point, right? So we keep it enclosed, under vacuum, great benefit for odor management, and also allows us to get that drying at a lower temperature, thus needing less energy input, right? So we will take that off, bring it to a condenser. We'll manage that condensate in a liquid form to process, manage any contaminants that might be collected, at that stage, and continuing on under that closed environment, continuing the augering process. We'll bring it up, and at that point, we will extract the dried material. Now, the system will have inline moisture sensors, so that we understand and can validate that the material has been properly conditioned to enter the gasifier following. And as we pull that material off, we'll continue with the remainder of the material on up to the top and introduce it back into the silo itself, right? So it's a closed system, very compact. Again, very few moving parts, nothing exotic necessarily, just a very, very novel design that is compact, requires very, very little energy, and we can operate this and support it really with the waste heat from the subsequent process that I'll describe in the next slide. But again, real benefit with low operating temperatures, low emissions, if any. Very simple design, and it also offers some safety advantages in that everything is contained internally to the system with little operator exposure, to the heated areas. And so when we bring that dryer into a flow diagram here, along with the HelioStorms, you can begin to see our notional design, right? And as we mentioned earlier, it accommodates a reasonably low output in comparison to a lot of other conventional drying or gasification technology that have been developed in years previous. And so when we look at it, we think kind of a starting point for us, we kind of level set. The beginning point is 50 wet tons per day. And that's 50 wet tons of a dewatered biosolids at a nominal moisture content of about 20%, which is an achievable volume by a whole host and a wide swath of the industry. We bring that 50 tons of material, introduce it, as you remember from the previous diagram here, and run it through the dryer. And from that 50 tons, we can take it down to 11 tons of a dried biosolid, pelletized dried form, and giving us about 78% reduction of the material there alone, and producing what most of the folks on this call would understand to be about a Class A product. We then take that 11 tons and we'll pass it through multiple HelioStorm units, right? So multiple HelioStorms are fed from a single dryer, and the importance of this is that while we have 3 to 4 shown here, typically we would always have some built-in redundancy and additional capacity at any time. Our system allows us to take the HelioStorm offline very, very quickly. In just a few minutes, we can take a HelioStorm unit offline. We can perform any maintenance, anything that needs to be done, to the unit. It can be accomplished with the remaining capacity still online, supporting the plant functions, right? And that's really intentional and kind of foundational to the design of an overall project, right? So we're trying to achieve maximum uptime, as little downtime as we possibly can. So having that built-in redundancy, having it developed and designed on a modular basis, allowing us to pull a unit off whenever we need to, really allows us to achieve that maximum uptime in support of the facility. Once we do that, we're going to generate that char that I mentioned a few minutes ago. And, we're going to go from about 50 tons down to about 3 tons for a total typical 93% feedstock reduction. Now, interestingly, let's go back to the syngas, because that is such a essential and valuable part of the overall process. We can harvest and extract that syngas, from the HelioStorm operation, and draw it into a genset and produce the electricity we need to go back in and feed the units themselves, right? So we're going to make from that 50 tons of biosolids coming in, we're going to be able to generate around 600 kilowatts of electricity, right? Not only that, there are multiple points at which we can extract waste heat from this process. Take that waste heat, feed it back in, and it's sufficient to support the LTC Dry process as well. So what you're looking at here is probably nearly energy neutral. Now, that is not to say that the entire project would be, because there are some ancillary pieces of the process and the project that are not depicted here, such as carrier gas generators, oxygen generators, cooling systems, augers, all those things like that. So this is probably going to be about 60% of the plant's needs. We have another 40% of the plant balance of plant power needs that are going to need to come from probably grid power. But our commercial model will accommodate that so that the client is never impacted by that factor. So whether it's a 40%, 20%, or 80% matters not to the client. Our commercial model will accommodate for that and account for it, and the client will never witness any variability and any exposure or risk at all as a result of that. I'm sure there'll be a number of questions about this, and we can return to it in a few moments, but I'm going to continue on in the interest of time and touch on that comment that I made a moment ago. And the versatility of the HelioStorm is really remarkable. Now, I've been talking this morning or this afternoon about our focus on the municipal biosolids vertical, and that really is where we're starting the commercialization process for the technology. From the biosolids stream, we can generate the syngas and the char that I've alluded to throughout the conversation here today. However, it's important to note that the HelioStorm really, as long as it's fed a properly conditioned feedstock, the platform really doesn't know the difference, and it really has a wide range of applicability to just a host of different feedstock materials, such as biomass would immediately come to mind, and certainly it would accommodate that quite well. Heterogeneous waste such as MSW would be another great candidate, and we have lots of discussions about that. Probably most interestingly, we are involved in one of the hydrogen hubs that are sponsored by the DOE, and HelioStorm has been accredited with the lowest cost of hydrogen production, but we can take methane drawn from a conventional anaerobic digester, and we can draw that through the HelioStorm and produce an extraordinarily clean and valuable hydrogen product, and are advancing through a project to do just that as we speak today. Very excited about that, and we think there's tremendous potential and upside on that vertical going forward. So just a wide range of feedstocks, and quite honestly, we're approached by lots of folks on a regular basis, and it's really kind of interesting, some of the ideas and the things that we haven't ourselves even thought of yet, but would certainly have applicability, and we're very excited to explore those as they continue to emerge. I'm going to ask Brandon to walk us through the next series of slides, because these are all interesting and exciting ideas and technologies, but we have undertaken a very prescriptive process to validate the technology against, the thing that probably is most interesting to this group today, which is PFAS destruction. So, Brandon, if you could, I'd like you to kind of walk the group through some of that strategy for us.
Absolutely. So, as Jim mentioned, we are trying to sort of do this in a step-by-step manner and do it, with a plan. And this sort of started with, because of the involvement of INL, the original cogent gasifier testing took place in Idaho Falls, and we moved that from Idaho Falls to Murfreesboro back during summer of this year. But our first testing was sort of a screening. Let's do proof of concept that destruction of PFAS actually works. And so back early in the year, end of January, start of February, we did some testing on an M1 module, so a single module of plasma in that Idaho Falls laboratory, and then we completed that testing. We moved here to Murfreesboro, and since then, as we've gone through commission and startup of this commercial-sized M3 gasifier, we've continued to sort of look at PFAS. We did some char testing back in September, to send that off and have it tested. And then since then, we've also done a little bit more gasifier testing of the syngas for PFAS as well, and we're awaiting those results. I think the next slide will help make this. So if you see the first test, this was the test in Idaho Falls on the M1. And so this was done with Montrose Environmental. And for this test, one of the things we wanted to do was to spike those biosolids that we were using with firefighting foam to really increase the amount of PFAS in there. Because the idea was we didn't want to just depend on detection limits of the PFAS in the syngas to sort of give us an idea of what our destruction efficiencies were. We wanted to put enough foam in there that you're sort of guaranteed to at least find some PFAS in the syngas, so that you can really do that mass balance and do some good calculations. And the results were that for several of the PFAS compounds that are found in the AFFF, they were greater than 99% of the destruction removal efficiency. And the other compounds that are in the AFFF all ranged, the rest of them ranged in that range between about 93% up to 99%. And so these were very good results for us, especially considering that it was just a single M1 unit, and considering how high that we spiked those level of PFAS in there using the foam. So we were fairly excited about those tests. The next test that we mentioned here is having PACE Analytical. We sent them some char samples, had them analyze them, and those came back as non-detect for PFAS using a method 537. And then more recently, since then, we engaged Mastardi Plot to come out and do sampling of the biosolids, the char, and the syngas, to again do additional PFAS testing. Those results aren't back yet, but one of the interesting things as part of that is that we did have them bring an FTIR so that we could look for what compounds were in the syngas, so that we could look for minor species. And predominantly, we were wanting to look for the fluorine and see what form the fluorine from the PFAS compounds were coming out in the syngas as. So go to the next slide, please. So the interesting thing was that we actually did not detect any fluorine compounds in the FTIR. So no hydrogen fluoride, no carbon tetrafluoride, no carbon hexafluoride, no sulfur hexafluoride. Those were all no trace measured on the FTIR. And to sort of go along with that, the chlorine and the fluorine that is also in the biosolids, those were non-detect as well in the FTIR. And so what this is telling us is that the ash minerals in the biosolids that are being fed, especially that calcium and magnesium, are reacting with those acid gas components in situ and forming stable salts or minerals there in the gasifier. And those materials are being carried out with the char rather than getting into the syngas. The other thing is on the left side, you can see that we do have a continuous gas analyzer on the HelioStorm. So when we're running, we're looking for those major syngas components, the hydrogen, the carbon monoxide, methane, carbon dioxide, water, and nitrogen, so we can continuously measure how much of those are in the syngas. And again, going back to what we said earlier, the interesting thing is because of the way the material is completely decomposed down to atoms and then comes back in that rapid quench exiting the plasma module, most of what ends up in the syngas is hydrogen or carbon monoxide. And so there's very high levels of those. The ratio between those varies a little bit depending on the carbon and hydrogen measurements within the biosolids themselves. But you do make this clean syngas that's very high in hydrogen and very high in carbon monoxide that can be then used as a fuel for genset. Or, if you start thinking about the idea of having a relatively clean syngas with high amounts of carbon monoxide and hydrogen, there's also other things you can do with that, that become interesting as well.
Thanks, Brandon. So the technology is very promising. It's very exciting and has generated a tremendous amount of market enthusiasm. When we contemplated bringing this to market, we believe very sincerely that, one of the most important parts of this would be the validation and the ability to not only validate it in the industry by virtue of installations in the field, but we don't believe that a utility manager should be asked or expected to take a flyer on a technology. It's difficult enough to navigate through the changing regulatory climate as it is, and then make the proper responsible decisions about a technology for that utility, and within that technology to select a responsible service provider that you could partner with for years to come. And we think the best way, the best vehicle to support that kind of decision making process is through an investment we've made in our own technology center located in Murfreesboro, Tennessee. This is a facility that is purpose built for a few things. It allows our our clientele to come and visit the facility and see for themselves and witness the operation of a commercial scale HelioStorm system in operation. And we've invested millions of dollars in this facility, and we have constructed it and designed it, and Brandon's team manages it for that purpose. It allows us to bring in a specific feedstock rather than have to make inferences about one feedstock against one that's already being processed elsewhere under different conditions, and allows that feedstock to be properly evaluated, screened, and tested in actual operation on a commercial scale, and allows us to facilitate the necessary sampling and analytics and other components of that process to allow for the most responsible decision making possible. And we're very proud of the facility. It was just commissioned this year, and it was a very successful event. We had tremendous attendance and interest, and that continues today. And we are already, as we speak, hosting clients and performing evaluations on those specific feedstocks. Pardon me, to gather the data that is desired. And we certainly hope that from this discussion and others that there will be interest generated, obviously, and if you find yourself inclined to explore the capabilities of our technology and witness the system in operation for yourself and speak to Brandon and his team firsthand, we certainly would be delighted to host you at our facility, and would be glad to talk about that with you personally. But let me show you just a few images here that I think are kind of interesting. Picture is worth 1,000 words, and here it is. Here is the HelioStorm frame as we were beginning to assemble it and commission it earlier this year. And this is our team in the control room, operating it, in real time. And as we said, even though this system operates at 3,000 to 10,000 degrees Celsius, understand that you can be in close proximity to the unit during operation. So you don't have to be separated from this unit by 3 brick walls and massive amounts of safety protocols and other things like that. It is quite safe to be around. That high temperature is contained in a very small, relatively small area and reaction zone, right? But here's the team operating it remotely, and when you visit our technology center, you can see all this for yourself. And of course, the ancillary equipment where we can bring in limited amounts of test volumes of material, bring it through the unit, and then collect the char, which is kind of behind there. So we can do that, as well as facilitating some of the sampling around the gas. We can document reductions of material from start to finish. We can even facilitate PFAS testing if the client so desires. And all of that data can be gathered and then can support further discussions with us and to include their engineering partners and the like. And so just a quick look into the technology center. This was phase 1. Phase 2 will be constructing the dryer, and that'll be up and operational in no later than Q2 of next year. And so finally, I'd like to wrap up here and just mention that in addition to taking the technical risk and facilitating a pathway for that, Heartland is prepared to take on additional risk that we believe is appropriate. And from a commercial standpoint, we are prepared to take on the risk of performance and guarantee the results of the system through a design, build, own, operate model, a BOO model, BOO model, if you will. We will design it and build it in-house, with some support where necessary from external engineering resources, which are going to be important relative to site engineering, relative to permitting, relative to a number of other areas, right? But that will all be done in-house and with our partners. We will own. We would like to own the system, but the important takeaway here is that we are prepared to site a project with no capital expected from the client. We're prepared to fund it and provide all the capital necessary for a project. And unless a client has access to some unique funding source, certainly we're flexibly minded enough that we would consider those types of things. And there's a number of ways to construct, that commercial model. But for those clients who prefer not to put up any of their capital at risk, we certainly are prepared to enter into long-term projects with those folks as well, and that should not be a deterrence or hindrance for anyone to consider our technology. And finally, one of the key considerations around this type of technology, or really any, is the staffing, right? It's staffing, it's retention, it's training, and we will, in addition to building it and to owning it, and we will operate the system with our certified, Heartland project personnel, right? So the client will not be burdened with any of the requirements around, operation of the system. It's a complete turnkey approach, and really, all we're asking for all of that is that a client would take that journey with us for several years of a contract term in order for us to allow the project to pencil out. And we think that's very attractive because we're prepared to guarantee cost trajectory for a client, upwards of 10 years as we sit and stand, today. And we think that's very, very attractive. It's generated a tremendous amount of enthusiasm around not only the technology, but the commercial model as well. And being in a position to have that certainty around the technology, certainty around disposal, certainty around costs of operation for decades to come. And that all pulled together, we think, makes the HelioStorm Biosolids conversion process extremely compelling and valuable to prospective users. And really that brings us to the end, Janine. I think that's the end of the slides, and we're certainly prepared to answer any questions.
Well, good thing, because there's a lot of them. And let's get right to them. Kelly's gonna help me facilitate them, and I'll keep an eye on and track the answers. And if anyone who hasn't typed in a question and wants to raise your hand, we can unmute you and you can ask directly. But I'm gonna have Kelly Murray from Heartland shoot some questions at you guys.
Great. Thank you, Janine. So first question for you guys. Is there a good understanding of annual maintenance and renewal cost, and what is expected in the cost?
Short answer to that is yes. Brandon, would you like to expand on that?
Yeah, I mean, we've been looking at those annual costs. I mean, ultimately the thing is there's not a lot of wear pieces of moving parts in the HelioStorm. So, the main maintenance cost on the HelioStorm itself is going to be those wear items, which is primarily the electrode tips. As those wear, you'll need to come down every few weeks and replace those. You'll probably want to inspect the internals a bit, and some of the graphite pieces that go inside may periodically need replacing. But yeah, the nice thing about there not being a lot of moving parts inside that gasifier is there aren't a lot of wear parts either. And the parts that can wear are relatively inexpensive. The main cost is in the power supplies, and those are fairly robust. So
great. Thank you, Brandon. Next question. At these high temperatures, how do you avoid ignition of the syngas?
So the main thing is the syngas would need to be exposed to oxygen to be ignited. And so you just keep the syngas contained within the gasifier and then within the syngas piping to the use. As long as that's airtight, you're not going to be getting air or oxygen in to provide that source to ignite it. Within the gasifier itself, we do use oxygen in order to increase the carbon conversion, increase the conversion rate of the material in there. But you're only adding that at a fraction of stoichiometry. And so because it's a strongly reducing environment with that high amount of hydrogen and high amount of carbon monoxide, any oxygen that's added ends up just being converted into that syngas. And so there's not enough free oxygen to actually cause an ignition. It's a very strongly reducing environment.
Thank you, Brandon. Next question. What is the wettest feedstock that you've run through the HelioStorm? Does the HelioStorm remove water?
So you can, this is an electrically driven system. And so, evaporating water in the HelioStorm is probably not your optimum use of energy, but we have run material up to, I believe it's about 50% moisture through the HelioStorm. So you can run high moisture materials through the system. But, again, there's an energy cost for heating and evaporating that water. And then because, the way we describe the HelioStorm is you actually decompose the feed material down to its constituent atoms. You also have to overcome that heat of formation of water to break it down into hydrogen and oxygen. So there is a bit of an energy penalty if you want to try to feed a very high moisture material through the system. But if it's appropriate for what you're trying to accomplish, it can be done.
Thank you, Brandon. Next question I have. I generate 140 tons per day. Does this mean that I will need 35 units?
140 tons per day. No. So the block flow that Jim showed was for the 50-ton plant. And so that was 4 HelioStorms for 50 tons, although that is having one spare. It's 3 in operation and 1 spare. So 140 would be 3 of those units. And so you would end up with about 9 operating gasifiers, and you'd have at least a couple of spares.
Great, thank you. Next question we have here. What pre-treatment of the solids is required before feeding the unit?
For the main thing, it's the drying step. As we mentioned, you can feed higher moisture material to the gasifier, but it's not the optimal use of your energy. So basically you want, feedstock of appropriate size and appropriate moisture to go through it. A normal Class A pelletized biosolids is perfectly fine. The only caveat I would add to that is, if you start getting those pellets over a certain size, if you started having 4 or 5 millimeter pellets or larger, you might want to go through a little bit of a roll crusher to reduce that back down to 1 or 2 or 3 millimeter pellets, just so that the pellets have time to react while they're in the HelioStorm. But other than that, that's the main feed prep that you need. It's just an appropriate size material for the gasifier.
A bit of a related question to that one, I would say, is how does pelletization occur in the LTC dry process? And are there constraints on particle shape, size, moisture content if using an existing drying system?
So I think we sort of hit on that existing drying system, and in the idea of you do want those sort of typical size pellets, 1 to 3 or 2 to 4 millimeter pellets. If it's oversized from that, you would probably need a little bit of light crushing to get it back down in that size. If it's smaller than that, that's okay, as long as it's not got a high percentage of fines. If you end up with 40 or 50% fine material, you might need to treat that a little bit before you put it in. On the LT Dry system itself, it sort of ends up being similar to other dryers, like a traditional drum dryer or something, where you have that very high rate of recycle. And so, once you feed that wet material in on top of the recycled material, you're essentially taking those small pellets and coating them with a little bit of wet material, and that wet material then dries as it goes through, and through the circulation rate itself. You have a little bit of attrition of the material, and so you kind of knock the size down a little bit. We're building the demo system here to get some more operating experience. The original pilot plant, the pellets that came out were typically around 1 millimeter.
Keep these questions coming. Whichever ones we don't get to, we will follow up with Heartland and get the answers out to you. So go ahead, Kelly.
Thanks, Janine. Lots of great questions.
Yes.
Next one here is, what is the typical residence time?
So the gasifier is, it's about refrigerator size. The actual operating, section is probably maybe on the order of about 5 feet tall, and pellets are falling through under gravity. So if you think about the largest pellets that completely fall through under gravity, the residence time for that would sort of probably be on the order of a half a second or so. There is, if you saw in the video on the right when we did the video, because of the plasma, because of the carrier gas that comes in, the environment is very, very turbulent. So, smaller particles are the smaller particles that are made from the larger particles as they fall through. Those will have a higher residence time just because they get caught up in those eddies and those vortices that form from that turbulence. And so, they may have a residence time on the order of a second or 2 or 3 seconds. But again, for the larger particles that can fall through under gravity, it's probably about a half a second of residence time.
Great. Thank you. Another question for you. Have you tested the char from biosolids for presence of micro or nanoplastics? In addition to PFAS, they are concerned for biosolids and accumulation therein. Thanks.
Yes, another challenge.
We haven't done that testing yet. Obviously, because of the way it operates, we anticipate that it'll do a good job of eliminating those microplastics as well. And the M1 gasifier in the Idaho testing lab was tested on waste plastic itself, and was able to successfully gasify that. So it was able to handle the larger plastic pellets, and so the microplastics that are in the biosolids, we anticipate that it'll handle those well, but we don't have testing proof of that yet.
Maybe 2 more questions if we have time for that, Janine, if that's okay.
Sounds good.
Does the syngas need any additional conditioning prior to entering the genset generator to produce the 600 kilowatts of power?
So there will be a little bit of conditioning. It's a fairly clean gas, but a couple of things. You do exit the gasifier, 14, 15, 1600 degrees Fahrenheit. So there is a cooling step to recover waste energy for the dryer. So you do have that syngas cooler in there. And in addition to that, because there's no cyclone, some of those biosolids pellets, as they fall through, will generate some very fine material. And so to protect the turbine, there probably will be a small Venturi scrubber to remove those fine particulates to make sure that you meet the gas spec for the genset. And on top of that, as we mentioned earlier, the FTIR testing showed that we were capturing the acid gases in situ on the char. But if it were a case where the ash minerals were a little bit different and you weren't capturing all of those gases in there, we would want to use a small caustic scrubber in conjunction with the vortex scrubber to remove the hydrogen sulfide from the gas, just to make sure that you meet that spec for the genset. And also, it's a little easier to do that pre-combustion cleanup of the sulfur in the gas rather than trying to do it post combustion.
All right. I guess our last question, since we're running against the clock here a little bit over. Let's see. To run a test in Murfreesboro, how much dewatered biosolids would you need?
So we've sort of set that up where it kind of depends on how much of a test you want. And there's different levels, but the easiest and the first thing would be generally to send us, something on the order of several hundred pounds of the dewatered biosolids. We would run them through the LT dry system and generate some dried biosolids. We would run that through the HelioStorm and show what the syngas composition was. But with say 500 or 600 pounds of dewatered biosolids, that would be enough to make a couple hundred pounds of dried biosolids, which would let you run. It's not a long time on the gasifier, but let you run the gasifier for an hour or two, and it would let you run the dryer for let me think about that, for 4 or 5 hours. That'd probably be the minimum. But this is something we've worked out this system, and Jim can probably provide that offline of how much material that we would need for these various levels of testing that we have established.
Yeah, that would be great, because I'm proposing I'll dump a list of all the questions that we didn't get to, and when I send out the link to everyone who registered, we'll try and get those answers from Heartland, if that's all right. Because
Sure.
we are
Absolutely.
running out of time. But thank you, everyone, Heartland team, and especially Jim and Brandon. We're all wishing you the best. And thanks to everyone who joined us today. We've started to pull together an exciting lineup for Lunch and Learn webinars in 2024. So watch for announcements on that. If there's something you're really dying to lunch and learn about, you let me know, and I will try to make that happen. Just send me an email. But thanks again for attending today, and happy holidays to everyone.
Thank you very much,
Take care.
Janine.
Thank you. Thank you.
Appreciate it very much.
Take care.
Thank you, Janine.